Welcome to Earth and Sky Camp. The hands-on learning activities that I'm going to show you can increase anyone's understanding of the world. Copying the manual map onto a basketball is the ultimate manual mapping activity. It gives students the best reference for further development of their mental maps, and it also reveals a lot about the geometry of maps. The type of markers used in making a globe can vary, but some materials are always necessary. These are a basketball, cardstock guides, a crayon, a sharpener, pencil erasers, rubbing alcohol, and paper towel. This is a kit for making a Sharpie globe. And this is a kit for making a globe with acrylic paint markers. Different colors and brands of acrylic markers and paint can be used. The simplest way to make a basketball globe is with Sharpie markers and a gel pen. One Sharpie must have a fine tip and the other a chisel tip. You start making a basketball globe by using a crayon to draw a grid of 15-degree wide squares. I'll show you later how to use the cardstock guides to make the meridians and parallels. Once you've drawn the grid, you'll use a fine tip marker to draw the coastlines of continents and islands. Notice that some lines have been thickened and some islands filled using the fine tip marker. This is because the chisel tip marker is less precise and shouldn't be used in tight spots. Also, notice that you can add 5-degree crosshairs to your grid wherever you need them. Do this with the Sharpie marker inside continents and with the crayon in the ocean areas. Now you can use your chisel tip marker to complete the land areas. I don't recommend trying to draw national borders on your basketball. You should locate cities on your globe. They can provide indicators for the locations of countries. You should only mark cities you can locate correctly in quizzes. You can always add new white dots to your globe in the future. However, the cities on your globe should accurately reflect your mental world map. The globe can then continuously reinforce your study of the world. Your globe will look even better after you erase the grid. It takes some effort to remove the crayon marks with a pencil eraser, but it won't remove the Sharpie ink if you've given it time to dry. Now let's look at how you actually draw the grid on a basketball. Remember, the manual map has 24 primary squares. They are each 60 degrees wide. The black stripes on your basketball are spaced 45 degrees apart. But because the manual map grid is based on 15-degree wide squares, we can regroup the squares to match the stripes. These stripes will correspond to meridians on your globe. All meridians are 1/2 of a circle. These circles divide the Earth into 2 even parts. The equator is also a circle that divides the Earth in half. Its location is based on the spinning movement of the Earth. The equator is a parallel, and all parallels are aligned with the spinning movement that causes our daily 24-hour cycle. Meridians are all the same size and intersect each other at the north and south poles. Parallels keep the same distance from other parallels and become smaller as they approach the poles. There are 2 common sizes of basketballs. Size 6 is used in women's basketball and for middle school students. Size 7 is the regulation size used in the NBA. The 2 cardstock guides in each kit have lengths that are half the circumference of the ball. The bottom edge of the rectangular guide is used to mark the locations of parallels on the stripes. The top edge is used for drawing the equator and marking where meridians cross it. The edges of the curved guide are used for drawing meridians and marking where parallels cross them. The air valve on a ball indicates where the equator crosses one of the black stripes. Align the 0-degree mark on the rectangular guide with the hole in the valve. Then Check that the 90-degree marks align with the stripe intersections on the top and bottom of the balls. Note that the 75-degree mark should align with the intersections of the curved stripes and their adjacent straight stripes. First, use the rectangular guide to mark the locations of parallels on the stripes. You can only mark half of the parallels along a stripe before you will need to move your hand to hold the other half of the guide down along the stripe. After you have marked the locations of parallels on all of the stripes, you will line the guide with the 0-degree marks. Use the edge of the guide to draw the equator. Only draw one 45-degree section at a time. You want to use the minimum amount of pressure to draw lines. Too little pressure results in gaps, but too much results in mistakes, thick lines, and broken crayons. Note that keeping your crayon sharpened results in the best lines, but crayons will easily break if they are too sharp. After you've drawn the equator, use the guide to mark off meridian locations every 15 degrees. You will use the edge of the curved guide to draw the meridians. Note that these guides should point to the stripe intersections on the top and bottom of the ball. Also note, you should always draw meridians with your hands positioned in the same way. For example, if you are right-handed, you will keep the guide positioned in the center with your left hand and will use the edge on the right to guide your crayon. You can then turn the ball upside down to position your crayon on the other edge. After you've drawn all of these secondary meridians, you will use the curved guides to mark the locations of parallels. You will then be ready to sketch the parallels. When you view the parallels from the top or bottom of the ball, it's more obvious that they are circles. I recommend that you sketch the 75th parallels first, because they are the smallest circles and they overlap the intersections of the curved and straight stripes. Then sketch the 60th and 30th parallels. Other than the equator, the shortest distance between the marks on the stripes is not along a parallel. The shortest distance veers away from parallels the closer they get to the poles. That is why airplanes do not fly due east or due west when flying to cities of similar latitudes. Once you've made the primary parallels appear circular, it's easier to sketch the others. For example, you just need to keep the 15th parallel equidistant between the 30th and the equator. Similarly, the parallel at 67.5 degrees is halfway between the 75th and 60th parallels. Use the 60th parallels to keep your 50th parallels circular, and the 40th will be halfway between the 50th and the 30th. The cartographic term for intersections of meridians and parallels is a quadrangle. The word just means four angles. Quadrangles are not squares or rectangles because they are formed by three-dimensional arcs of circles. You should see on your grid that the quadrangle between the equator and 15 degrees north and the quadrangle between 60 degrees north and 67.5 degrees north are both shaped like squares. However, the circumference of the 60th parallel is half that of the equator. That is why the darkened quadrangle at 60 degrees appears to have 1/4 the area of the one at the equator. Both quadrangles are 15 degrees wide, but the smaller one contains only 7.5 degrees of latitude, half that of the one at the equator. The lengths of degrees of latitude do not change, but the lengths of degrees of longitude decrease as they get closer to the poles. Despite the decreasing size of the grid's quadrangles until the 75th parallel, they are all roughly square. These quadrangles can all be sketched using the drawing by squares method. Be sure to click the Globe Grid button in the study mode to copy the squares onto your basketball. This will display what the longitude of the stripes should be. Most basketballs have logos printed on them, which you want to position next to the 180th meridian. You can match the stripes on the map by using either end of the ball as the North Pole, but only one end will result in the logo appearing below Hawaii. This also results in the least concealment of the Arctic coastline by the curved stripes. You will want to copy most of the squares from the largest scale maps. They will give you the best views of individual squares, and they will roughly show you what areas are concealed by the stripes. Beyond the 75th parallels, the coastlines of the map are extremely distorted and not useful for copying onto a basketball. It's much easier to copy these polar areas from maps. The gallery page contains polar maps that show the parallels at 60, 67.5, and 75 degrees. The parallel at 67.5 degrees is not standard. However, it's just 1 degree away from the Arctic and Antarctic circles at 66.5 degrees north and south. Antarctica is simpler to draw, but it's easy to misalign the meridians and rotate the coastlines 90 or 180 degrees. The prime meridian is at 12 o'clock here. Note that the ice shelves, which are colored white, can be ignored and not included with the coastlines. These are refillable acrylic paint markers, which you can use with any color of paint you want. The fine tip is similar to the Sharpie. The chisel tip is slightly smaller than the Sharpie I used on the previous globe. Then there is a wide-tipped marker on the right. The surface of a basketball is not ideal for marking with any type of marker because of the bumps. These bumps are called pebbles. Looking closely, we can see that a marker tip might not always contact the lower areas between the pebbles. This is one issue. The other issue is drawing precise lines on this surface. For example, if you were to try to draw an island with a wide or chisel tip marker, most of the paint would be placed on the tops of the pebbles. After 5 or 10 seconds, some of that paint might flow down into the lower areas. This can even happen with ink from a wide tip Sharpie. The key is to first use a fine tip marker, which makes more precise lines and releases less paint. As you continue to draw more coastlines, this paint will dry and form a barrier that wet paint or ink won't cross. You can then increase the width of the line with a chisel tip marker. However, in tight spots, you can avoid mistakes by increasing the width with more strokes from the fine tip marker. Also notice the black stripe on the left. You can see that it is painted on the ball because a streak of the orange rubber is showing from below. This is how the balls I used were made. More expensive balls use black rubber for the stripes. Also, notice the orange ridge next to the stripe. You sometimes need to use both fine and chisel tip markers to cover ridges and indentations. Don't use a wide tip marker this close to the stripes. There are several popular brands of acrylic paint markers such as Montana, Liquitex, and Decocolor. Montana makes the refillable markers with interchangeable tips. Any high-flow acrylic paint will work with them. The viscosity of the paint in all markers is lower than the acrylic paint that you would apply with a brush, and that is why there is that issue with it running between the pebbles. All paint markers work the same way. You push the tip into the barrel to get the paint to start flowing. A spring pushes the tip back out, and this pumping motion must be repeated 6 or more times to start the paint flowing. Note that the flow of the marker can slow and you occasionally need to pump it to maintain the desired flow. Also, when you stop painting for a while, you should put the top back on the marker, and before you start painting again, you should test the flow with a piece of paper. Know how much paint will be flowing onto the ball before making marks. There is also a steel ball in every marker. When you shake the marker, the ball keeps the paint ingredients properly mixed. You should also be aware of the relative size of the pebbles to the land you are drawing. The diameter of pebbles is more than 2 millimeters, which corresponds to about 70 miles on the Earth's surface. Most cities are less than 10 miles wide. Fine tip markers make lines slightly smaller than a millimeter. Their width corresponds to about 23 miles. The smallest line you can make with a chisel tip is 2 millimeters, and that's close to 65 miles on your globe. This means it's impossible to show fine details on your globe. It also means you have to exaggerate the size of cities so that they will stand out. This is an example of coastlines and lakes drawn with a fine tip Montana marker. Note that the marker represents the water along the coastline and not the actual coast. Also notice the crosshairs in the ocean areas. You will want to place your ball in something like a coffee cup to keep it still while you are painting it. Realize that you will place whichever hand you don't hold the marker with on the ball to turn it as you are painting. If you are right-handed and touching the ball with your left hand, you will want to continue painting on sections to the left of what you've just painted to avoid touching the wet paint. Use a chisel tip to fill in all of the areas that are too small for the wide tip. These include the edges of the black stripes. Painting the lower surface between the pebbles is much faster and easier with the wide tip marker. However, the larger volume of paint can easily flow onto stripes. Minimize mistakes by using the right tip in the right place, and you will finish more quickly. The cities were made on this globe using the same type of fine tip marker as I used on the coastlines, but with white paint. Note the cities on the black stripe. The stripe is roughly 200 miles wide. You want to balance keeping cities close to their actual size with making them large enough to see from a distance. It's easy to make them too large because the amount of paint that flows out the tip can vary. Most mistakes can be quickly removed with a piece of paper towel. Dipping the towel in water will remove larger mistakes. After the white paint has dried, you can erase the crayon grid with a pencil eraser. The light blue areas show where the chisel tip marker should be used. If you can't name a city, wait until you can before you add it to your globe. Cities not only provide references to their countries, we can reference lakes, deserts, and other physical features using the closest major city. 2/3 of the Earth are covered by oceans. Painting the oceans makes for a more traditional globe, but it's more difficult to draw islands. This is a size 6 and size 7 basketball. They were both painted with cerulean blue, but using different brands of paint, Golden and Liquitex. Compare the detail of the Caribbean islands with the same islands on the Sharpie globe. On the other hand, lakes are more difficult to draw when the original orange surface is used to represent water. However, drawing this type of globe is faster and less work. Being able to identify the cities on both types of globes is the key to their usefulness. There are a variety of colors that can be used, but high contrast is necessary between the ocean and the land with the cities. Note that the coastlines on this ball were drawn with a green chisel tip Sharpie. Its ink appears bright green on paper, but it turns very dark on the orange rubber surface. However, it may be a better choice than a black Sharpie because white cities will still stand out and there's more contrast between the dark green and the black stripes. Ink from blue Sharpies will also appear very dark. You will likely make a few mistakes whatever type of marker you use. Nobody will notice some of them, but you should know how you can correct them. Crayon grid lines can be removed with a pencil eraser. You may at first see some discoloration in the orange surface after you have removed them, but this is just eraser residue that can be easily removed with an old toothbrush and water. The stiffer and larger the brush is, the better. Wet paint can also be easily wiped off with paper towel, but it can dry fairly quickly. The best way to remove paint or ink is with rubbing alcohol. It works with both ink and pencil erasers. The pencil erasers that slide onto the end of a pencil or pen enable you to efficiently erase small mistakes. Pour some alcohol into the bottle's cap and dip the eraser into the cap. This greatly increases an eraser's ability to remove both ink and paint. When you erase with rubbing alcohol, you are diluting the paint into a liquid that sits on the surface. That's why you then need to use paper towel to wipe the ball's surface. After the paint is removed, you will then need to wash the residue off with water and a brush. The concept of scale is important in making maps and globes. This size 6 globe was made with a Sharpie, and the size 7 was made with black acrylic paint. We say basketballs have different sizes, but we say globes have different scales. When we use units to give the scale, such as 1 inch equals 873 miles on a size 6 ball, that's called a verbal scale. You will also see fractional scales printed on globes and maps. For example, the ratio of 1 to 55,721,600 means that whatever number of units of distance that you measure on your globe or map is 55,721,600 times larger on the actual Earth. This is called a fractional scale. It is easily converted into a verbal scale using metric units. 1 centimeter equals 557 kilometers. The concept of scale on map projections is more complex. The spherical three-dimensional surface of the Earth is projected onto a geometric shape that can be flattened to form a two-dimensional map. There are a variety of geometric shapes and many ways of positioning them to make different types of maps. The Mercator projection was designed in 1569 in response to the explorations of Western Europeans. Its map grid is based on where parallels would be located if a cylinder was wrapped around a globe and contacted the surface at the equator. An imaginary straight line from the center of the Earth determines where a parallel on the globe's surface will be placed on the cylinder. The cylinder is then unrolled to make the flat two-dimensional map. Note that a line passing through the poles will never contact the cylinder, and parallels above 85 degrees will be spaced at distances too large to be included on the map. On this Mercator map, meridians and parallels are spaced 10 degrees apart. At the equator, quadrangles are square, but at 60 degrees north and south, they are twice as high as they are wide. This corresponds to the proportions of quadrangles at 60 degrees. Because the 60th parallels have a circumference which is half the distance of the equator. The circumference of any parallel is equal to the cosine of its latitude multiplied by the circumference of the equator. This is why cylindrical projections have variable map scales. Note that a fractional scale is also usually given, and it refers to whichever parallel of a globe was in contact with the cylinder. This is usually, but not always, the equator. Bar scales are used for large-scale city maps. A graphic bar can be used anywhere on a city map, but you have to take note of the latitude of a parallel before you can use a variable scale to calculate distance on a cylindrical projection. The success of the Mercator projection was based on the fact that although it distorted the relative size of areas, it preserved the direction between them. With a compass and a sextant, Mercator projections could be used to navigate the oceans. Over 1,000 years earlier, Ptolemy had made a map of Europe, North Africa, and Western Asia. Mercator incorporated this information into his map. The Mercator projection then provided a tool for documenting maritime discoveries and completing the knowledge of the Earth's surface. Before Ptolemy lived, people understood that the position of stars and the sun in the sky were related to the latitude of their own location on a spherical Earth. They noticed that the altitude of the North Star was related to how far north they were. When they eventually sailed south of the equator, the North Star dropped below the horizon. However, explorers could only estimate the longitude of locations until the invention of the chronometer in the 1760s. The word chronometer was the original term for what we now call a pocket watch. It enabled explorers to finish accurately mapping the world. For example, when the sun was at high noon on the island of Fiji, the chronometer revealed that it was midnight in London. That meant London was 180 degrees away on the opposite side of the planet. The world rotates 15 degrees every hour. 24 times 15 equals the 360 degrees of the whole Earth. Actual time zones are often based more on political relationships than on longitude. For example, China is more than 60 degrees wide, but it only has one time zone. However, when the sun rises in Shanghai, it's still dark in West China. This is what a modern Mercator projection looks like. The North Pole can't be seen, but Greenland is almost as large as Africa. Its shape, however, is actually quite accurate. This animated GIF shows the size distortion on Mercator projections. The scale of the map gradually increases as latitude increases. Geography textbooks often recommend the Robinson projection over the Mercator because it more accurately shows the relative sizes of areas like Greenland and Africa. There is still some size distortion, but it's much less than the Mercator's. Note that the North Pole is represented by a horizontal line that is more than half the length of its equator. A sinusoidal projection does accurately reflect the relative sizes of areas. The lengths of parallels correspond to their cosines, but the further areas are from the central meridian, the more distorted their shapes will be. An interrupted sinusoidal map solves this distortion problem. If you could peel the rind off an orange in one piece and flatten it, the orange rind would have gaps, like an interrupted projection. Atlas maps of areas that are in the mid-latitudes are typically shown with conical projections. Notice that parallels are represented by arcs of circles, and meridians come closer together as their latitude increases. These maps are similar to what you see on globes, but they can only show small areas. Conical projections cannot be used for world maps. Google and other computer maps use cylindrical projections of the world that distort the relative sizes of areas. However, most people use Google Maps to view cities and state highways. Google City Maps are based on data from the U.S. Geological Survey. They make their city maps with transverse Mercator projections. In a standard Mercator projection, the cylinder contacts the Earth at the equator. In a transverse projection, the contact occurs at the central meridian of a city. This results in very little distortion for the small number of degrees of a typical city. Projections can also be constructed with purely mathematical relationships. This pseudo-cylindrical projection is not based on the relationship of the spherical Earth and the cylinder. All quadrangles simply contain 10 degrees of longitude and latitude and are perfectly square. The manual map projection is also constructed mathematically rather than geometrically. There are either 15, 10, or 7.5 degrees of latitude in a square. This approximates the preservation of direction and shape of a Mercator projection, although it's not as accurate. Its advantage is the ease of constructing its grid of square quadrangles and the ability to use existing grids of squares on which to make maps. Its format of 24 squares also provides a system for memorizing locational information.